In this video, I am going to demonstrate the use of the force model in analyzing vertical accelerations. So for this example, I'm using an elevator that's held in place by a supporting cable. That's a tension T, we'll call it. And this elevator is a mass of 500 kilograms. And what happens in this problem is when we press the button to go to a higher floor, there will be an upward acceleration. So at rest, on a certain floor there's zero acceleration. When you press button higher, like 10th or 11th floor, if you're lower the floor, we need to accelerate upwards from rest, and that acceleration rate is going to be 2 meters per second squared. The question is, what is the tension in the cable that will allow you that 2 meters per second squared? So first step, draw a free body diagram. So for the free body diagram, here is a picture of the elevator, and one force is a T for tension. The other force is mg, the weight of the object, pointing down. And that's your free body diagram. Those are the two forces that are acting. So step 2 of the force model is to write the forces in the template here from the diagram. So I'm going to state that the positive x direction points to the right and the positive y direction points up. So if I look at the diagram here, I see no arrows or vectors, force vectors pointing left or right. So this is 0. There's 0 forces, therefore there's 0 acceleration. So that we know that's 0. I'm not going to move to the side here. In the y direction, I see two forces. A tension that points up, so that's positive T, and an mg that points down, so that's minus mg. And it will be accelerating, so again, we put x there. It's not 0. The only number we should put in here is 0. If it's not 0, we just cross it out, because there will be an acceleration rate. That's the way you want to phrase that to yourself. Third step, solve. So we're going to solve for T. So here's my equation. I just built a custom equation for that tension. So I'm going to go up here and write that down. T minus mg equals ma. And so if I solve for T, T is equal to mg plus ma. And if I plug in the numbers here, I'm going to get 500 times 9.8, because that's the value for G, plus 500 times 2. And this is 4,900 plus, this is another 1,000 here, equals 5,900 newtons. And that's the answer. So a couple interesting things here before we wrap up. Imagine the acceleration were 0. Imagine this term here were 0. So this whole term would be 0. The tension in the cable would just be the weight, mg, which makes sense. If it's not accelerating, there's just the tension is the weight, mg, which would be 4,900 newtons. But because it accelerates, you would think there's an extra push on this, or extra tension or extra force on this thing, because we need to accelerate upwards. That extra force is right here. It's the ma that we added on. It's that extra 1,000 newtons of force needed to accelerate it. If the thing was more massive, this were 1,000 kilograms, this would be larger, it would need a larger force. If the acceleration were larger, if we really wanted to accelerate that elevator up, that'd be, again, extra tension on that cable, and that would be larger as well. So you can see the effect of the acceleration on that tension, which makes sense. If you yank something, that's when the string or cable is likely to break, because you have this extra force there. Second thing is, people might be wondering why the 9.8 is not negative, because I put a positive 9.8 there. It actually is negative. If you kind of go back to the diagram, this G points down. The reason why this arrow points down is because gravity points down. So this arrow right there is the negative of the negative 9.8. That's why we put the negative sign there. That's the negative of the negative 9.8. So it's out here, not in the number. And because I moved the mg to the other side of the equation, right here, moved it to the other side, that negative became a positive. So G is still negative. It still points down, hence the downward pointing arrow. That's a negative sign. But algebraically, when we move it over, the negative sign disappears. So that's why it's positive 9.8 when you plug the number in. And that's very typical. When you solve these problems, you're typically going to move things over to the other side of the equation, and that negative sign will disappear. So that's another example of using the force model, Newton's second law, to solve problems involving forces and accelerations.